Well, we just left off having computed not just the eigenvalues, but the eigenvectors in a situation where there's a complex eigenvalue. And so one of the things that I want to kind of touch on before we dive into the next page is that these eigenvectors, if you see what Maple sometimes spits out, they may look a little different, but remember, eigenvectors can be written in multiple ways. So for example, this eigenvector, I can multiply each one of these values, or each one of these essentially elements, by the same value to get an equivalent eigenvector. So for example, if I multiplied this top number by I, and I multiply the bottom by I, so that would be negative 1, so that would be positive 1. So that's equivalent to this eigenvector, I1. So these two eigenvectors really are the same thing. They're pointed in the same direction. Just like this could be rewritten as, if I multiply the top by I, the bottom would be negative 1. So they're equivalent. You can write them however you want. But notice, no matter what you do to this one, it's never going to appear to be that one. Right? You can't turn this into that, no matter what you do. They really are two different eigenvectors. They're complex conjugates, but they're eigenvectors. So on the top of the next page, we're going to address the question of what can I do to rewrite these straight line solutions in a real form. And in order to do this, we have to kind of take a slight little side trip to the land of Euler one more time, our old pal Euler. If you remember, Euler is well known for finding and inventing all kinds of stuff in mathematics. He's pretty famous for being the first person there to lots and lots of stuff. And one of the most famous formulas that he's known for is what's referred to as Euler's formula. And Euler's formula has a bunch of different variations, but it basically says if you have E, the natural base, to the complex number a plus ib, or a plus bi if you want to think of it that way, you can use the properties of exponents to rewrite it like this, e to the a times e to the ib, and then you can turn this part of it right here, can be rewritten as this. There's the magic of Euler's formula. He says that for e to the I times a real number, you can rewrite that as the sum of a cosine and a sine. But notice there's an I that's a coefficient on the sign here. And so after all is said and done, you can kind of multiply it out. But this is the magical step that you definitely have to memorize, right? So what does that mean for us? Well, it's going to allow us to turn this exponential and multiply it through and do something kind of interesting. So keep in mind that what we're dealing with here is not just e to the a plus ib. This is e to the a plus ib times t. There is a t there. So I just want to make a note that we're dealing with e to the negative 2 plus 3t. Oops, negative 2 plus 3t. Negative 2 plus 3i. I times t, right? And so that means the a and the b are negative 2 and 3i. That would be 3i. So just keep that in mind. Sometimes people get hung up on that when we're doing this. So what we're going to do is we're going to leave this in kind of matrix form, and we're going to multiply the exponential through into the matrix, and then we're going to expand each one of these using Euler's formula. So I'm going to kind of scoot this equal sign over a little bit so that I've got a little bit of room here. And so in the top, we're going to have I times e to the negative 2 plus 3i times t. And so that's going to turn into e to the negative 2t times e to the 3it. Hopefully you can see where that's coming from. That's this step right here, right? I'm kind of splitting things. And I'm multiplying the t into each term. And in the bottom, that's just e to the negative 2t times e to the 3it. So for a first step, all I'm doing is I'm taking my straight line solution and trying to rewrite it, kind of simplify it, expand it, I guess is another way of saying it. So let's continue this, continue our work, and we can expand for each one of these exponentials with a complex number inside of it. We can expand using Euler's formula from above. And so that's going to be equal to, and the top line, it would be I times e to the negative 2t times all this stuff. So it would be cosine of the b, which is in our case 3i t. Oh, I'm sorry. I just got done saying be careful of what you select. The I for us is not part of the b. I'm sorry. Apologies if you're following along and you spotted that. Good on you. That the b is just the number. It's the real number there. Sorry, it's just the 3. So I'm getting ahead of myself. So this right here is just going to be cosine of 3t on the inside there. Apologies. Right? So there's cosine of b plus I times the sine of b, which is 3t. And so that's my top row for this. And this whole thing right here, that's coming from Euler's formula up above. And the bottom row is, it's going to look exactly the same. It just doesn't have an I sitting out in front of it. So it's going to be e to the minus 2t times cosine 3t plus I sine 3t. And again, that bottom row is coming from, or that that term is coming from Euler's formula. Okay. And so now what we're going to do is I'm going to multiply this out. And in order to save a little bit of space for myself, I'm going to multiply it out over here. I'm not doing anything else other than kind of multiplying through inside here. So it's just going to be I times e to the negative 2t times each one of these terms. So the first one would be I e to the negative 2t times cosine of 3t. And then I times I makes a negative 1. So this will become minus e to the minus 2t times sine of 3t. So that I that was in this kind of blows up when it multiplies through with that other I. Down here, there's no I to multiply through, so nothing really changes. We just have e to the minus 2t cosine 3t plus I times e to the minus 2t sine 3t. And at this point, you might be thinking, okay, great, how does that help? But if you pay attention to kind of each one of the terms, every single one of these terms has an e to the minus 2t going on. And only this guy in the top line, in the top element, and only this guy in the bottom element have an I value, an I factor. So what I'm going to do is I'm going to take the I term here and the I term here, and I'm going to kind of align them, line them vertically up. And you'll see why here in a second. So I'm going to suggest this is exactly equal to I e to the negative 2t cosine 3t, and then minus all this stuff that's left over. And in the bottom, I'm just going to take this guy and move him first. I'm going to put him first in the order. So it'll be I times e to the minus 2t times sine of 3t plus this, what's left over here, e to the minus 2t times cosine of 3t. And so all I did was I put my terms that have an imaginary value in them in front. Now, if you're looking at this and thinking, okay, how does that help? Remember that a matrix like this can be pulled apart and split into kind of two parts, if you want to think of it that way. So really, I could rewrite this as the first part's going to look like this. I e to the minus 2t cosine 3t, and in the bottom I e minus 2t sine 3t, and then plus negative e to the minus 2t sine 3t, and e to the minus 2t cosine 3t. And you're thinking, okay, still not seeing how that helps. Or maybe you're catching on. My trick here is this I is actually a constant. It's just a constant. So I could factor out the I. And really what we have here is two parts distinct from each other. They're not linear multiples of each other. I have a solution is made up of two parts. One of them just has a constant multiple of I. Another way of saying this is we actually have two components of a solution. This is the real part of my straight line solution number one. Oh, that's not the real part. That's the imaginary part. Oh, I got it ahead of myself. I probably need to take a break after this video. So that's the imaginary part of y1, and this right here, that's the real part of y1. So in a way, it's like a plus bi, right? Where there's my a plus b times I. I'm essentially saying that this straight line solution has a real part and an imaginary part. And so my argument is our straight line solution y1 is made up of a real part plus an imaginary part. And by way of our friend the linearity principle, since that imaginary part really just has a constant multiple of I, I'm showing you that I have two distinct solutions tucked inside of this one particular solution. And it's a little cheeky, it's a little hand-wavy, but we're going to make the argument that since I know these two are distinct parts, that I actually have all the information I need with this one straight line solution. I have all the information I need with this one straight line solution to come up with the general solution, which is factor out that I and just multiply by a constant, and you have everything that you need for your general solution. And we're going to see how that works on the next page in the next video. And I'm going to take a break and probably put my leg up and put some ice on it.